Let's look at the learning intentions and your success criteria. We will be learning how to write logic statements and analyze them. You will be successful if you are able to solve at least one question on your own. Let us begin today's lesson by recollecting what we learned in the previous class. We learned about 6 different logic gates, and they are the AND gate, the OR gate, the NOT gate, the NAND gate, the NOR gate, and the XOR gate. Let's take a brief review of what we learned previously. The basic gates are the AND gate, OR gate, and NOT gate. The AND gate gives an output if both the input conditions are true. By true, we refer to 1 as the value. For the OR gate to have an output, any one of the input conditions has to be true. For the NOT gate, it inverts the input condition so that the output is opposite of the input. The 3 derived gates are the NAND, NOR, XOR. For the NAND gate, it is actually an AND gate going out into a NOT gate. For the NOR gate, it is an OR gate which is being output through a NOT gate. And the last one is the XOR gate. It is an exclusively OR gate. It is similar to the OR gate, but it has an exclusivity in the input. I hope you remember these truth tables. We'll try to discuss them in the current slides. Let's look at what logic statements are. Logic statement is a statement that describes a logic circuit. You know what a logic circuit is, don't you? A logic circuit is a combination of 2 or more logic gates. So when you keep one logic gate, it just becomes the truth table of that logic gate. But if you connect more than one, you have a logic circuit, and a statement describing this circuit is called as a logic statement. Now, the third point is that logic statement has the input combination that makes the output from a circuit. We'll look at examples so that you get thorough with this point. We previously discussed about the input being present considered as a true value. For the input to be true, we consider the value as 1. We also say it as an ON state. When the input is not present, it is represented as 0 or false or off. Although we don't say this much, but this is for your basic understanding. We mention when the input is present and when it is true and when it is on, as well as we mention the value as 1. To understand logic statements, we have to break it down into 2 parts, the output side and the input side. When the input conditions are satisfied, the output can be defined as true. Let's look at an example to understand what we just referred here. The statement Z equal 1 if A is 1 and B is 1. In this, the Z equals 1 can be inferred as an output, and A is 1 and B is 1 is referred to the input. So what we can understand is that there are 2 inputs A, B, and one output Z. For the Z to be true, A is true, B is true. There has to be an AND gate in between them. So this statement can be rewritten as Z equal A and B. To write logic statements, we need the input part and the output part of a logic circuit. So we'll just try writing logic statements for the basic gates and then pick up on bigger circuits. So first we have the AND gate. So you can see A and B are the inputs and Z is the output. So this can be written simply as Z equal A and B. This is quite similar to the example that we discussed just now. So for this statement to be true, there's only one condition. Both A and B have to be true. Only then Z becomes true or the output becomes 1. This is evident from the truth table for AND gate which we learned previously. Here you can see only this statement is true. Z has a value of 1 when B is 1, A is 1, or Z is true when B is true and A is true. The second gate with us is the OR gate, and we have the inputs as A and B, and the output is Z. So how do you think that we can write a statement for this? Let's give it a guess, and by the knowledge from the previous statements, it could be very easily done. You can write as Z equal A or B. For this statement to be true, either A or B are true. Now this word has an importance, either. That is, A can be true while B is false, A can be false while B is true, or both can be true. Only then an output will be there. There is 3 statements for the condition to be true. We'll discuss that in the truth table. As you can see, the first statement where both are false, there is no output from the logic gate. And when there is one true condition, B is true, then you have a Z as true. When one of the input is true, that is A is true, again we have an output from the OR gate. And when both the conditions are true, then we definitely have the output. So these are the 3 statements valid here. The third gate with us is the NOT gate. This is a simple single input, single output gate, and we have A as the input and Z as the output. So by just guesswork, how do you think you can write this as a statement? We know Z is the output, so it starts with Z, and then you put an equal and you write the gate and the input. So simple as it is, Z equal not A. Now here the output is the opposite of the input, or we'll say that inverted. Inverted means making it upside down. So if we give the input as 1, the output will be 0. And if the input is 0, the output becomes 1. So Z is whatever that is not A. Now the truth table, if you can recollect from the previous class, is just 2 statements. If you give 0, you get 1. If you give 1, you get 0. Those were the 3 basic gates: the AND gate, the OR gate, and the NOT gate. Now let's look at the derived gates. The first derived gate is NAND gate with the input A, B. The output is Z. So to write it in simple logic statement, Z equal A NAND B. We know that the NAND gate is an AND gate with a NOT at the output. So you can rewrite it as Z equal NOT A and B. The statement says that Z, or the output, is the output of AND gate passed through a NOT gate. The AND gate is having A and B as the input, and the output from the AND gate goes through a NOT gate to give the Z. Z is true if A and B are the opposite of an AND gate. This can be verified by the truth table. This truth table we learnt in the previous class already, but again we'll just go through it and verify that in the case if A and B were passing through a AND gate, it would have an output only for the last statement 1 1, and then there should have been a 1, but because of the NOT at the edge, the 1 becomes a 0, and all the first, second and third statements which were having 0 as the output through the NOT gate, it becomes the 1s here. I hope this is clear because we learned it in the previous class about how the NAND gate derives this output. Let's look at the next derived gate, NOR. The inputs are A, B, and the output is Z. Similar to the previous NAND gate condition, we'll write it as Z equal A NOR B. And we can rewrite it as Z equal not A or B. This statement shows very clearly that A or B comes out through a NOT to get the Z as output. The statement says that Z is the output of OR gate passed through a NOT gate. The input of this OR gate is A and B, and that when it reaches the output of the NOT gate becomes Z. Z is true if A and B are the opposite of an OR gate. From the logic circuit of OR gate, we know that A and B will be 0 0, then OR gate will give us 0, and OR gate will give 0 1 as 1. OR gate for 1 0 will give a 1. OR gate for 1 1 will also give a 1. And for NOR gate, this is passed through a NOR gate, so the 0 in the first statement becomes a 1, second statement's 1 becomes a 0, third's 1 becomes a 0, and the fourth one also 1 becomes 0. And that is how the NOR gate gives this output. Let's look at the last derived gate, XOR. This is having A, B as the input and Z is the output. So the logic statement can be written simply as Z equal A XOR B. Now Z is true if A and B are the exclusive of an OR gate. Like we said before, this is similar to OR gate except when both the conditions are true. Then there is a confusion, and in that confusion there will be no output. Usually for OR gate, when both of the A and B are true, there will be an output. But in an XOR gate, if both A and B are true, there will be no output. This is evident from the truth table. When only one condition is true, we get an output. So this is an exclusivity of the OR gate condition. To convert a logic statement into a logic circuit, we need to break it down into input and output parts. Let's take a look at the example given, X equal A or B and B and C. Take a special note of these brackets which are specifically to mark the input conditions. From this statement, it is clearly evident that X is the output, and the input conditions are referred to this big bracket, and there are smaller brackets defining parts of the input condition. Now, by looking at this, we can deduce that A, B, B, C are the four inputs. Since B is common, so we can say that A, B, and C are the three inputs. Now, looking at the smallest or innermost bracket, we can see that OR gate separates A, B. Another innermost bracket shows that an AND gate separates B, C, and a bigger AND gate separates these both statements. To start with it, let's start drawing the outline. Here you go. We have A, B, C as the inputs as we discussed right above, and X as the output. By looking at the smallest brackets first, you can start assigning the gates as a rough work. So the most smallest innermost bracket is A or B, says that there is an OR gate between A and B. So we'll just place an OR gate in between the A and B lines over here. Now the next innermost or the smallest bracket is B and C. We have an AND between B, C. So we're going to place the AND gate here between the B and C lines. Next, we have seen that there is an AND gate between these two brackets, or the AND gate is taking these brackets as inputs. So the top bracket is A or B, and that's this OR gate, and the bottom is B and C, the second bracket, and the output of these two should go into an AND gate, so we will just place it roughly over here. Now let's just make the connections. First to the OR gate, A or B. Next, B and C. Now let's connect this two brackets to the next part. We are connecting it to the AND gate. So that becomes A or B and B and C. Now to take the output finally equal to X. So that basically is how you translate a logic statement into a logic circuit. Let's look at how to write logic statements from a logic circuit. Here we have a similar logic circuit, but please note that the gates are very different. We have A, B, C as input and X as the output. And for the same reason, the logic statement will begin with X equal to, because X is the output. Now just look at these statements and we'll just break it down. So we can see that there is a OR gate in between A, B. So A or B, let it be there. Let's look at this one. The lower part has an OR gate and a NOT gate. B or not C, that's how it comes. So B and not C goes into an OR gate, so it's B or not C, and finally there is an and between them. So we'll just write x equal to A or B. Then it comes out to the and. The next part is B or not C. Okay, so I hope this one is clear, and we're using the double bracket on the outermost side so that specifies the output part. As we end today's lesson, let us try to solve few questions, and you can show it to your computer science teacher at your school. So there will be one type of question from logic circuit to logic statement, and another from logic statement to logic circuit. So please get your textbook, page number 64. On page number 64 in the textbook, there will be exam type questions, and the second question, A part, it has a logic circuit, and the question is to write the logic statement. It's quite easy. I hope you find time to solve this one easily. And next, one more question is there. The third question, you have to draw the logic circuit for this specific logic statement. So please do the second question A part and third question and show it with your computer science teacher to get your remarks. The question is on textbook page number 64 of your grade 9 computer science textbook. Once again, question number second, A part, and question number 3. With this, we come to the end of today's session. I hope this was useful for you, and please make use of the time available with you to solve these two questions